Welcome to our last lesson for Chapter 3. So, today we're going to be putting all of these skills together, okay? Seeing how this chapter kind of all works hand in hand. So, interpreting computer regression output. So, on the AP test, usually they're not fans of making you type like long lists into the calculator, okay? Because they don't like running the risk that if you type one number in wrong, now everything's wrong and they can't track why, okay? So it's much more convenient for them to show you a Minitab output like this, okay? And so more often than not, you're going to be just using data from this to answer all of your questions, okay? So, for example, here, if I'm asked to write the least squares regression line, okay, y equals, now here, these are the two values that I'm looking for, okay, the coefficients. So the coefficient of whatever the variable is, that is my slope. All right. The constant, well, the constant is just the number that's by itself. All right. So those are two things that you have to make sure you can pick out of a Minitab output. Be able to pick out the slope and the y-intercept so you can write me the equation of the line. You should also be able to pick out r, okay? Now, the question or the thing is, you're not going to see r. You're going to see r squared. So what can you do with that? Well, if I'm given r squared and I want r, what can I do? Well, I can square root it. So really quick, let's square root the 0.606. Now notice I'm not square rooting the percentage, right? I'm turning it into that value between -1 and 1, and I'm square rooting that. So my r is about 0.78. Now, something to pay careful attention to. Notice my slope is negative. So that means my r should be negative as well. My r takes the same sign as my slope. Okay, so make sure that you know that to check your slope to make sure you're putting the correct sign on r. Okay, because otherwise you could get that backwards and then that could mess up some calculations or interpretations that you're supposed to be doing. So correlation and regression wisdom. Okay, so just some things to make sure that you've picked up on along the way. The distinction between explanatory and response variables is important in regression. Okay, so knowing the difference when you're calculating the line is a huge piece. But remember, for R itself, it doesn't matter. Okay? Correlation and regression only describe linear data. You can't use it for anything else. Correlation and the least squares regression line are not resistant. Both are heavily impacted by outliers. And association does not imply causation. Okay, so just because we can model that there is an association between the two does not mean that one is causing the other. That we have to do experimentation, and that's going to be coming later in the course, more in second semester. Two things I want you to keep in mind. An outlier. An outlier is an observation that lies outside the overall pattern of the other observed values. Points that are outliers in the y direction but not in the x direction have large residuals. Other outliers may not have as large residuals. Now, the difference between that and an inflection point is or not inflection, influential. An influential point is influential for a statistical calculation if removing it would markedly change the result of the calculation. Points that are outliers in the x direction are often highly influential for the least squares regression line. Okay, so influential doesn't necessarily even mean it's an outlier, but it means that when you remove it, it'll greatly change your calculations. All right, so two things I want to make sure that you're aware of. just that language in case it comes up. So, what is our big picture? So this slide right here basically encompasses all the things that I want you to know, okay? So first, can a set of data be modeled by a regression line? First thing you want to check is check the scatter plot, check the residual plot, okay? Those are going to be the first two things that you want to check before you start looking at saying yes or no if the data is linear. If the scatter plot looks linear and the residual plot shows no pattern, then interpret R, S, and R squared. R, again, should be between 1 and -1, and basically what it tells you is there is the strength, direction, and that it's a linear association. R squared, you want close to 1. Remember, R squared is the percentage of the variation in the response variable that is accounted for by the regression line. S should be small, and what it's saying is on average, how far is each observation from its predicted value. So if each of those also pan out and are appropriate, then you can make your regression line and say that it models that data. Okay, this is kind of the accumulation of how this is building, what we've been working towards. Everything in this chapter is all about determining if something is linear or not, and then describing it. So let's do an example that uses every one of these skills. Long-term records from the Serengeti National Park in Tanzania show interesting ecological relationships. When wildebeests are more abundant, they graze the grass more heavily, so there are fewer fires and more trees grow. Lions feed more successfully when there are more trees, so the lion population increases. Researchers collected data on one part of this cycle, wildebeest abundance and the percent of grass area burned in the same year. Results of the least squares regression line on the data are shown here. All right. So what they're showing us is they're showing us a scatter plot on the left, the residual plot on the right, with the Minitab computer output of this. So let's go through and answer these questions. So first, give the equation of the regression line. So remember, we need to know how to pick out this information. The slope is always a coefficient with the descriptor. All right, so negative 0.05762x, and my y-intercept is the coefficient of the constant, the number that's by itself. All right, and this is predicted percent of grass burned. X is going to be wildebeests, and we're talking in thousands. All right, so let's talk about slope. What does the slope of this regression line mean? Again, slope being the value with the x. So what is a good interpretation for it? So for every 1,000 additional wildebeest. Now, why am I doing 1,000? Well, because when x increases by 1, the wildebeest are being counted in thousands, okay? So that is something that's very important too, is note if there's any unit like that. So here when x increases by 1, really that's 1,000 wildebeests, okay? And the percent burned is predicted to decrease by 0.05762. It decreases by the y value because it is negative. All right, so the correlation. So here, r squared is 64.6. So again, you can square root that to find r. So square root it, And make sure you remember it takes on the same sign as your slope. And what does it mean? Well, it means there's a strong negative linear association between wildebeest abundance and percent of grass burned. Okay, just like I outlined on that previous slide for you. R squared and S. R squared, on average, an observed value of percent grass burned is 16 away from its predicted value on the line. Where is that coming from? That's coming from right here. Okay, that is where your S is. And R squared, R squared means 64.6% of the variation in the percent of grass burned is accounted for by our regression line. So now the real question, the build in all of this, is a linear model appropriate? Okay, I would say yes, yes it is, because let's look at everything here, okay? Our scatter plot shows a linear pattern. Our residual plot doesn't show any pattern. And our R value is negative 0.8, which is showing a strong relationship. So I think all of those things brought together would let us say that it is appropriate to use a linear model for this data. Okay? So you do want to address each of those things. On the test, you are going to be asked this. Okay? I'll tell you that straight up. And when you are, you need to make sure you have an appropriate answer. And that is showing evidence such as this, talking about you can see a linear pattern in the scatter plot, that there's no pattern in the residual. R is relatively high, okay, or in this case, close to -1. All of those things, okay, are helping to indicate that this is linear data. All right, so now that is all for our notes. We are done with, yes, we are done with our third chapter. So again, please make sure you ask if you have any questions on this, especially because this last section was basically the accumulation of everything. So just make sure that you contact me, you ask me if you have any questions on this. So again, thank you for watching, and I look forward to reviewing